I love that dinging. Yes. So, in case you guys didn't see my shirt, wanted to show this off a little bit. I'm pretty proud of it. So this is one of my office shirts. I have a couple. This my sister got me for Christmas a couple years ago. This is Dwight Schrute, one of the main characters in the show. If you haven't seen it, throughout the show, he has just ridiculous dress costumes, certain roles that he plays, and these are all different scenes. Like this one, he's dressed up as his Recyclops. That's how he promotes recycling. Yeah, this one right here. Yeah, the scene of the classic scene where he cuts off the face of the CPR doll and wears it. That's like one of the greatest openings for the show. That's like this one. For what? If it's really quick. Yeah, also that. Belschnickel, Pennsylvania Dutch Christmas. The Scranton Strangler. This one I don't know. It's just him with a mustache. Huh?
I remember they.
Oh my gosh, you're right. The Nashville branch.
I forgot.
Yes, they go under disguise and they.
It bugged me all day.
No, it wasn't Nashville because that's where Holly was.
Utica branch.
Utica.
The Utica branch. Well, I don't know what they call it. They break their copier. That's what it is. Yeah, this one is. They have the flasher in the parking lot, and Pam convinces Dwight that he's the suspect. It's just a picture of him with a mustache. That one's good. When Jim convinced Dwight that he was in the FBI, and then convinced him his cover was blown, so he had to dye his hair, and so they bleached his hair. So yeah, just wanted to let you know what my shirt is in case you didn't know the show.
We actually watched The Office last week. Well, I did. And I watched
Really? What class?
Simpson.
Marketing.
Marketing?
We watched.
Was it when they take Michael to
No, we just watched the first 2 episodes.
of the entire show?
Yeah.
Oh wow!
Because
gonna be every
just
Friday.
like an introduction. Well, because he said that sometimes we might watch it like in there.
For marketing stuff or just for fun?
Because it's his favorite show.
He told us we were gonna watch every
So he just shows it in class?
Yes.
No activity or like goal?
No.
What the heck?
It's a show. You can't expect that.
Well, I want to do that, but we can't.
It just depends on the day. Because most of the time we do something.
You gotta just find something that connects to it. Something.
You know, we could. We can watch Office here, and if you guys do the homework, or I can just assign readings, we can make a flipped classroom and do physics at home and just watch Office. We're not going to do that. As a first-year teacher, I don't think that would fly so well. That's good. That's actually legitimate. We could do that sometime.
But is it true though that if something explodes in space, it wouldn't make a sound?
Correct.
That's
Well,
what I thought.
yes, because
There's
what
no
sound
atmosphere.
what sound is you propagate like it's a wave.
Yeah.
When you make a sound, you're moving the air molecules, and it spreads out, and that it's a wave, a vibration. That's what you hear. Your ear membrane, it vibrates, and that's how you interpret sounds. So if something blew up in space, there's no air molecules, there's nothing to vibrate for that sound to be transmitted.
Yeah.
So you wouldn't hear it.
Something blows up and it goes like big. Now, would like fire still work?
Well, what do you need to have fire? To have combustion.
You have to have oxygen, and so when things explode,
You need a hydrocarbon.
It wouldn't actually explode. It would just kind of fall apart. Or...
You're right. Unless you have some like a hydrogen tank, and you spark or that gets open, you have hydrogen to burn. You could have an explosion there.
Yeah.
But you're right. There might still be an explosion from whatever you started with, but it's not. The flame won't shoot out because there's no air.
It would just dissipate really quick.
Yeah, yeah.
Like
It looked really boring, like terrible CG graphics in a movie.
Yeah.
Just like, and then it falls to its pieces. Yeah, because there's no atmosphere. Yeah, that's right. So, fun fact for the day.
Our imagination. What else is on this?
So we left off talking about this, right? We did 1C, didn't we?
We got through that one.
You guys finished this one. The then I was looking at average versus instantaneous. That was the cars. So, one, I guess I'll start. Are there any questions you guys have from anything we talked about last class? I just noticed your backpack is Sparko, and that's awesome. I just now saw that. Side note, you know Momo steering wheels, like detachable ones? I've always wanted to make one with like a custom like groove as a security feature, and I'd take my steering wheel in when I go to the store. That way I just leave my car unlocked and no one can steal it because I can't drive it.
Well,
Super side car note. That's
if you
awesome.
don't leave your key in it, cars nowadays are a lot harder to steal because they're like if you have like a push start button or something like that, because they're harder to like they're harder to start or steal or whatever.
They're harder?
It's like a sensor.
Yeah, last thing I heard.
Yeah.
If your key isn't in it, then it's not like you can't just go up and like hot wire it like you can like.
Which is a good thing because if a car is newer and it's got more technology, I sure hope it's more difficult.
And then also like you can't. I don't know, like because everything's so like hard to take apart and work on.
See,
with
someone
newer vehicles.
tried.
Oh, yeah.
My mom was walking on the Cardinal Greenway, and someone tried breaking her window with a rock. You can see scratches in it.
Are you serious? Oh my gosh.
Welcome to Marin.
You're right.
Dang it, I live there. That ain't good.
I barely.
Yeah, Marin's not necessarily the greatest place to live.
Marion is really interesting. There's Iwu. Super nice. Super
And then
safe.
everything else is a ghetto.
Super nice.
There, all right, so
Everything
there's
outside.
Iwu, and then there's like the little, then there's John's neighborhood. And that's about the only safe places in Marion. Now, I will say, I don't think over by the hospital is horrible, like over there on the, you know, kind of where Olive back there on the
Not by the hospital?
It's close past that.
Not really.
Yeah, it is. It's
That's
actually
like in the video.
All right, so back to physics. What we're doing is worksheet 1D. Its velocity is a vector. Again, I do this because I want you guys individually to wrestle with and get through as much as you can of what you know, process it individually, and then I always like to come back because I want to make sure that we're all on the same page. If there's any questions, I want to address them first, and my goal for that is to like prevent misconceptions. If you think about something wrongly, I don't want that to happen over and over, and then you realize what's the correct, physics way. That's kind of why I do this. But take time to work through this. Again, it's worksheet 1D. Velocity is a vector.
How are you wanting us to label positions since they're both running it from opposite directions? Positive in their direction?
That's a good question. So if you get this guy. So if we're looking at this top part, John was asking, how do you label their positions? This is the trick where this is one reality, right? They're running in the same place, but I need to define what my directions are, my position. So I would have to make the decision, I'm going to call this 0, and this 15. So, was it Angela would start then at 0. Blake would start at 15. I could flip it. I could say Blake starts at 0, and this is the positive x direction, and over here is 15. You can do either. You get the same answer. Physics still is physics. It's just you flip it and do it differently. So pick one orientation, and then you have to leave it, and then you have to answer those questions based on what you defined the position is. That's a good question. Don't forget this one's got a backside. All right, let's work through this together. If you're not quite done, that's all right. What we're doing now is we're looking at two different motions in the same area, in the same scale. We define this, and then we use it to analyze both their motions on the same scale. And that's important. We'll see what happens. We also, velocity is a vector, we'll get to draw out specifically this velocity is a magnitude, it's a size, it's a number. It also has direction. So when we look at this, Angela's position, she's over here. We'll do her red. She was running at 3 meters per second, right? Blake was, no. She's 5, isn't she? Alright? How do we want to define our coordinates, our position? Where are we going to set our 0? What do you guys think?
Where Angela is.
Alright, so we're going to say this is 0. Alright? We are going to set this as our coordinate system, and all of our answers are based on this coordinate system for both Angela and Blake. You could have done it backwards. You could have said this is 15, 10, 5, and 0. Totally valid, but all your answers have to be based on that coordinate system. You can't flip coordinate system because then you're describing motion for two coordinate systems in the same space. That doesn't make sense. So we define it and then use this to write all these physics terms and explain their motion. So 0, Angela's at 0, right? She's starting at the 0 point. Where's Blake at? He starts at 15. After 1 second, where's Angela at? 5. How'd you know it's 5? Yeah. After 1 second, Angela's run 5 meters in that 1 second because her velocity, her speed's 5 meters per second. After another second, He's run another 5 meters and another 5 meters at 3 seconds. You can also take their speed times how long they've been going, right? 5 meters per second times 3 seconds. Well, my seconds cancel out, and I'm left with 15 meters. It's another way you could do that. Blake, after 1 second, what position is he on our scale? 12. He's running this way. His distance, his position's decreasing because it's going this way on our scale. It's 12 because every second he runs 3 meters. So after 2 seconds, he's at 9. Another 2 seconds, he's at 6. Does everyone agree with that? Oh no. Gonna run out of power. Does that make sense? Fortunately, I'm gonna have to move this. Oh no, I can't. Give me 1 sec. My computer's dying. Also, fun fact, I'm throwing my wife under the bus a little bit here. My wife, for Mac chargers, she thought this is all there was to it. She did not know what these are for, to wrap the cord. She had no clue. She's had her computer for like 2 years. She had no idea that you can change this and basically put like an extension. She had no idea. And I was floored. Like, you've owned this computer for 2 years. So at least I was able to teach her something. Oh, it's going to barely reach. There. Okay. Okay, so sorry about that. Now, when we go to plot this, it's really easy. I'm going to take this away. These were our data points. So at 0 seconds, at 1 second it was 5, 2 seconds it was 10, 3 was 15, right? And that's Angela, right? We just take our data points and put them on a position time graph. Blake, at 0 seconds, he was up at 15. 1 second, he was down at 12. 2 seconds, he was at 9. 3 seconds at 6. Does everyone agree with that? Right? Now we need the slopes of the line. How do we want to do Angela? We know it's a straight line. So we can pick any 2 points. What do we want to do?
0, 0.
We want to do this point, and what other point? We need 2 points to get the slope.
The next one.
Want to do this one? How do I find the slope? In this case, the y-axis is position, delta x, over delta t. What's delta x? Final position was 5. Her initial position was 0. Final time was 1 second. Initial time was 0. What are the units of the slope of the line for Angela? Meters per second. The rise is meters. The run is in seconds. Does this look familiar? Where did we see 5 meters per second in this worksheet? Yeah, that's how fast she was running. As a reminder, the slope of a position time graph is your velocity. Blake is the same way. So if I do final 6 minus initial, he was initially at 15. Final time was 3, right? That makes sense? What's this negative sign mean? Why did I get a negative answer? Yeah, that's one reason. On our graph, negative slope of a line goes down as we go in the positive direction. Physically speaking, why is it negative?
Because he's going the opposite direction of Angela.
Yeah, specifically of what we defined as the positive direction. We counted from 0 to 15. Well, Blake was over here going the other way. He was running in the negative direction. Therefore, his slope or his velocity is negative. There's your vector. Positive 5 meters per second is a magnitude in a direction. That positive implies this direction. When I throw that negative sign on, I now indicate this direction. So whenever I see that and I look at my coordinate system, I know how fast and I know what direction. It's a vector. It's got magnitude and direction. What'd you guys put? When we did that. How about this backside? Did you notice what the units are for this graph? What the axes are? Come on. You guys got this. Just shout it out.
Meters per second over second.
Yeah. This is time still. It's right here. This should be 0. That's a big typo. But now we're not doing position versus time. We're doing velocity. How would I plot Angela's velocity? Well, what was her velocity? Positive 5, and it was the same all the way through, right? How do I plot that? So she started at 0, or at 5 meters per second, right from the get-go. How fast was she running at the very end? How fast was she running at 2? How about at 1? That is a plot of Angela's velocity as a function of time. At any given moment, she was running at 5 meters per second. It was a constant velocity. It was the same all the way through, and it was positive. It was in our positive x direction. Huh?
How could she be running at 5 meters per second at 0?
Because as soon as you hit 0, like you've started. So you're moving that speed, but no time has passed to actually let you cover any distance.
Okay.
It's a little weird. Technically, you're right. Technically, at 0 seconds, right here, she's right here.
Yeah.
And as soon as you go to 0.00001 seconds, it instantaneously jumps up. So you're right. Technically, this is correct, but it also gets really tricky. Is this possible? Could someone start at 0 and then the instant after 0 passes be running 5 meters per second? That would imply infinite acceleration. That'd be like being stopped on a highway and then instantly you're going 60 miles an hour.
That'd be amazing.
Do you understand? Infinite acceleration, your car would like fall apart. Nothing would be able to withstand that. So the reason we don't do this is we like imply that at 0 meters and 0 seconds, as soon as one that's passed, she's at a constant speed. So if you really dig in, you're right. But we approximate it because it just told us she runs at 5 meters per second the whole time.
This is kind of like where it works on the graph, but doesn't really work in real life.
Right. This is a super simplified physical situation. It's an idealized. In physics, we're going to idealize things a lot. We're going to make things really nice, really cushy, so that the math is simple. Because if you had to consider what actually happens, it would look something like this. She would have to start running and build up speed and then be at a constant velocity. We're going to get there, but that's a lot harder to do.
This is just for basic understanding.
Yes. Yeah. This is a super controlled, super idealized situation so that we get these basics and the concepts are a lot easier. Real physics is really difficult. Like if you get college level PhD, if you do research, you do actual physics, one, you super specialize. You pick something super specific and you look at just that thing. And it's really difficult because you got to consider everything. To model the real world as it actually is mathematically is very difficult. We'll get to some of those difficulties again, idealized, but it's a good insight. But for now, as soon as she starts, she's already at 5 and it's the same all the way through. All right, how about Blake? We calculated -3, right? So I have to plot -3. And it's the same all the way through. This is a velocity time graph. This shows their velocity as a function of time. The other graph was position versus time graph. That showed where their position was as a function of time. Both of these graphs describe the exact same motion. It just points out a different variable, a different physical quantity. How about this last part, this argumentation? Do we agree with the claim? The point on the position time graph where the two lines cross represents when Angela and Blake are at the same position and traveling the same velocity. Do we agree with that claim? No. There's something wrong with that claim that's not correct. What do we agree with about it? When we look at where their position was as a function of time and we see that they cross, what does that mean? So Brody's saying they were at the same position, yes, but that doesn't mean they're at the same velocity. Do we agree with that? Let's try it. You said the position's the same because they have the same position. Well, what is it? I know. It's redundant to, I don't like that, but what was their position when they crossed? Go figure, I already erased it. Angela was this, ended at 6, right? Yeah. That's pretty close. Actually, that's really good. That's really good. Right here. They're at the same position, aren't they? When we look at time, If we stop time, they're at the same position. They're going different directions, but they're at the same spot at the same moment in time. Well, what is this? T equals 1.9, right? 1.2, 1.4, 1.6, 1.8. Yeah, 1.9. What about the position? 9.5. We like that? So this will be a little messy. But down here, they have the same position, because they have the same position of 9.5 meters at 1.9 seconds. We can support the claim that they have the same position. Now, Brody said that, however, they do not have the same velocity. How do we know that? Well, look at the slope. This slope, Angela, was 5 meters per second, right? What was Blake's? -3 meters per second. They don't have the same slope. Their velocity was different. Even though they're at the same spot, they're running opposite directions. Right away, their velocity is not the same. Even if they were both 5 meters per second, if they're different directions, those are two different vectors. Velocity is a vector. If it's the same number, I don't care. You need to look at the same magnitude and direction if you're going to claim that two vectors are the same. So that's why the velocity is different, because the slope of the line is, we had 5 and 3. Oh, that's a terrible 5. 5 and 3. Again, this is looking at, there's a claim being made. You can't make a claim in science unless you have evidence and reasoning to support it. Half of that claim about the position we can support with our evidence. The evidence was they crossed. That means both are at the same position. There's my evidence and the reason to support, yes, they are at the same position. However, if I look at the slopes of the line and look at their velocities, they are not the same. So even though they're still here, they're different velocities. So I refute this claim. Here. I refute that because I have evidence that says otherwise. All right? Sometimes you would have to make that claim, and you need evidence and some connection of why your evidence supports your claim. Brody. You're right. This is technically negative. Thank you. Thank you. Angela was a +5. You just leave it blank. Brody was, or Blake was -5. Or -3. Darn it. Am I, so one, Ethan and John, am I boring you?
No, I'm listening.
If this is too easy, that's fine. But if I'm being boring, I can jazz things up a bit. I don't want to. Please don't make me. But if it makes sense, that's fine. Does anybody have any questions about this? Again, it's hard to know how much you guys know, how easily you understand this. So if I'm babying you guys, just move me along and be like, we get that. I just want to make sure everyone understands this, especially starting physics, like super basic. This is all foundational. Because we'll learn kinematics. We're describing motion. We don't care how they're moving. When we go to dynamics, then we look at, well, what force was applied to cause that motion? Huh? Okay. We'll end up getting rolling because, again, this class we got a lot of material. But I want to take a lot of time to make sure all of this clicks. If you have any questions, I want questions. There's no stupid question if you genuinely want to know the answer. I don't care if everyone else thinks it's a stupid question. I want that question so that I can address it and help you guys as best I can. All right? That's probably a stupid question. Especially because you demonstrated. I claim that's a stupid question because when I did attendance and said Brody, you responded.
Ooh.
Therefore, that's a stupid question.
Maybe he has a brain tumor and he forgets.
Maybe I'm short-term memory loss.
It only works at being in class and then you lose it.
I don't have it written down on my paper.
I know you were being sarcastic, and that's why I called it a stupid question.
I know.
If you legitimately want to know, it's not a stupid question. That's the entire point of a question, is to know what the answer is because you don't know. And again, I don't want you guys to feel like you can't ask a question in this class. I don't care what other people think of your question or of what you know or don't know. If you don't know, my job is to help you understand, and your job is to understand and have a better grasp. All right, so we'll get this cleared off. Oh, wait, 1 sec. We just did. Okay, pause on this worksheet. So I passed out worksheet 1E. I'm going to have you just pause. Get out your MacBooks. I have a quick simulator that I want you guys to do. Also to help break up just doing pen and paper work. I apologize, I totally forgot that I have this queued up. So what I want you guys to do, and again, virtual students, this link should be in the assignment that the YouTube video of this class will be posted. It's this first one. What I want you guys to do, and I don't think I posted it to your guys' class, darn it. What I want you to do, I'll show you how to get there. All you guys look up physics aviary. Aviary, I think, is a bird house. Isn't that right? Or a bird zoo. So the physics aviary. Oh, yeah, there you go. Classic Google. My roommate from college, he lives in New York and works for Google, so he's a software engineer. Now he works for the YouTube team, but every time there's an issue with Google, or sometimes like Google like crashed temporarily, and I sent him a screenshot and I told him to get back to work, I always blame any Google problem on him. So if you Google physics aviary, it'll be the first one. This is one, I'm going to use this a lot. There's a lot of neat specific simulations that are really cool. And you guys can also, feel free to look through this. Go to the first year section and this advanced motion ideas. Oh, wait. No. Sorry. First year and graphing motion. Yeah, this one. It doesn't look like you can click it, but click the picture. It'll launch this. And then you guys put your name in, and then hit, I think, desktop, since you all have your computers. Oh. What's that, John? Keep it down a little bit. It's the, velocity graph matching game. And then put in your name. It doesn't really matter. I'm going to have you guys do this. You are given a velocity time graph. We just made those. This tells me what my velocity is over time. Now this is going to be a bit of a challenge because we've only seen constant velocity graphs where it's the same all the way through. This changes. It's a line though, we can calculate it. So if it's a flat line, what does that mean about the velocity? Stays the same. It's constant. So I just chug along at the same speed. What's happening here? My velocity is decreasing. Again, I'm pushing you guys. We haven't seen this yet, but does anybody know a physics term or name for this? My velocity is decreasing. I'm slowing down. Do you remember what the term for a change in velocity is? We haven't talked about it. How do you get up to speed on the interstate? What does that do to your car? What's the accelerate? So deceleration or negative acceleration. We'll get into that, but you're slowing down, you stay steady, and then you accelerate, you increase your velocity. What your challenge is, so I'm going to set this to random numbers, and I set my acceleration, brake, and speed. If I start this, I'm already way messed up. So you see how my initial speed was way lower than what I'm trying to emulate? And then what you do is you hit the gas and brake pedal to control your car and try to get the same motion that graph has. So I messed up. If I push the gas pedal, my velocity increases. It goes up at a steady rate. I did not do well. My motion was not even close to what I was trying to do. So how do you do this? How do I start at this velocity? Well, don't I have to set my initial speed? Well, what is that? That's 35, isn't it? So to do this correctly, I would have put 35 here. Because I'm going to start here. As time goes by, again, it should all be random. You guys will get a different one every time, just FYI. How do I know how much I brake? Aiden, do you have a quick question? Find it? He was physics theory. First year, the graphing motion. Yeah, D. And then it's the velocity matching. Yeah, that one. Click it, and then put in your name, and then it should get you right in. How do I know how much this decelerates? Yeah. How do I know what the hint slope of this line is? You just do the math. You just do the math. We're not doing position versus time. We're not looking at how the position changes versus time. We're looking at how does the velocity change with time. So I calculate my slope, do final minus initial over the time. That should give you a meters per second, the rise, divided by the run, which is in time. So it's a meter per second, or meters per second squared. Again, all this is leaping ahead, but it's simple enough. That's your braking rate. Whatever rate that is, that's what I need to put in, and then I'm going to hit my brake at the right time. If I did it right, it'll follow that line, and then I let it go. I let my car just coast. And then I need to figure out what's this slope. Do the slope, rise over run. That's your acceleration rate. You're speeding up. That's what the gas pedals do. You don't need negatives because it already says braking rate. All right? I just refresh it and then go back in. again, I'm doing my math. My situation will be different. I hope I did that right. So I calculated my acceleration should be 3. My braking, oops. It knows it's a negative because it says braking, or it'll say like deceleration. That would be the slope of the line. You want to know how much does my velocity change every second? If it decreases by 5 meters per second every second, I would put 5 over there. So I just calculate the slope of that line. So let me see if I can. I'm off to a good start. Holding the brake. Let it go. Ooh, a little late. I'm doing pretty good. Boom. I did pretty darn good, not gonna lie. I was a little nervous I did my math wrong. You guys watched me.
I was doing mine, so I couldn't see it.
So this was the graph that I was given, and I had to figure out how do I replicate that motion. I needed to figure out what my starting speed was, and I set it. I calculated the slope of my deceleration. How much does my velocity decrease every second? And set it. My braking rate when I push the brake pedal in the car. Then I just let it be and it coasts. And then I need to accelerate, hit the gas. I do the slope. How much does my velocity change every second? We'll just do rise over run. It changes by 3 meters per second. Goes up by 3 meters per second every second. That's my acceleration rate. And then I just needed to push the pedals at the right time. Did everybody else get it really darn close? Pretty close? You do a good job, John? Maggie, did you get yours?
No, Maggie sucks.
Ooh, I don't know. She kind of straight up crushed this right now. Yeah, she crushed that one. So this, to me, I really like this. This is fun. I'm a car guy, so that helps. But this is really neat to get to drive a car, but in like a physics context, and having to do math to figure out how do I get my car to do that same thing. Did you crush it? Yeah, it's pretty fun. And then you got to do the timing, so how good is it? I wish it would spit out like a percentage, like, oh dang, that is good. I can't even see the red line underneath. That's impressive. Did everyone get a chance to at least try this? If not, I want you guys to at least get a chance to try it once and see how close you get. The things you need to figure out is what speed do you start at? How does your speed decrease, that deceleration, the slope of this line? This is easy. You just let off the gas and the brake. And then when you hit the gas, what's the slope of this line? How much does your velocity increase over time? If you set all those parameters, then you just got to get the timing down.
Full car?
You can't read this line.
Aiden, yeah. Ooh, that's pretty darn good. Yeah. This one, I think you just like press it just a bit too slow. But your calculation, all of that was good. That's perfect. That's sweet.
Let's start this.
All right, so hopefully you guys have at least gotten a chance to try it. Go ahead now, and then we'll do this next sheet. I gave you 1E, relative velocity. Move on to that worksheet. If you're still finishing up the simulation, at least try once, see how you do. This was a really cool one. One to kind of preview, we're going to get to acceleration. It's really simple. It's not position time. We're now looking at velocity time and how that changes. So now this relative velocity, now it's going to look at two different velocities that are basically combined. So go ahead and work through that, and then we'll again touch base on that one.
Rip John. Yeah, it's pretty close. Let me see how fast it's taking.
Way fast.
Oh wow. Oh wow. Still going.
Yeah, I took it up to 500.
Yeah.
You don't see it though.
Right on the ground. It's
But you see it at the top part.
we don't want to break them. Go. Wait, we need somebody to get on meters converted to miles per hour. Or meters per second. I don't think this thing has a limit. I think you can just keep on going up.
Alright. How many meters?
Right now I'm at like 1,500. It's 1,500.
That's about 3,355 miles per hour.
Oh, so where are you? Where are you like?
2,000 and 4,473 miles per hour. Are we supposed to do this? We did, yeah, we did.
Yeah.
No, we're supposed to do.
It's not a race, it's a marathon. I mean, it is a race, but it's
Racing too.
that's just the line to win.
That's 11,184.68 miles per hour.
We get your acceleration. And then we'll just accelerate. What the heck? We can't see even the car moving. We glitched out the car. I can't see the car.
That's only 6,000 miles per hour shorter than
The speed light.
than a spaceship.
Oh. Oh yeah, we need to go to the light. John is ho 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 ho. You look if you're not happy with your work, otherwise you're an instructor. Oh no, I'm gonna do it all. I just don't like typing it. That's stupid. I just want to type it in.
What?
Now we gotta get it all the way to 5,000 again.
Are you guys cranking up the acceleration?
Yeah,
We added a 5,000.
but we couldn't see the car moving. It was just the signs going by.
Andre, just
Oh,
click
for
it to-
goodness sake.
Listen, we
That's
had-
what you guys spend your time on?
I actually have an excellent question, alright? So,
Oh,
This has nothing to do with this.
actually,
Like, maybe it's
I love your math.
a
So there was like a train going like 80 miles an hour, and a train going 40 miles an hour, and they collided. So wouldn't this be like a force of 80 miles an hour and a force of 40? Like, how would you figure out like how much force would be?
That is an excellent question. I would agree with you. We will literally do that in this class.
Yeah, we're gonna get 2 trains.
Yeah, where are we gonna find the trains at?
Okay, we're not gonna okay. We're not gonna literally drive trains into each other. But his question was, if you have 80-mile-an-hour train and 40-mile-an-hour train, how do you figure out like how much force each of the trains has on each other and like the total energy? We're gonna get into all that. We're gonna look at the momentum of each train, and then you look at the momentum of the train unit after they collide.
So, like,
You can look at the force,
the weight as well. That have an impact.
No way.
the mass.
Yeah. So like, if the train was
Rather
like
than stick.
20 tons, the one that's going 80 miles an hour was like 20 tons, and the one going 40 was like 60,000. Well, it's like 60 tons, then.
Yeah, that what you're asking is momentum.
Yeah.
When you look at the momentum of two objects in a collision, the momentum determines what happens, who wins. And we're going to get to that. Because if you have a huge mass and a little velocity versus, say, a lot of velocity but almost no mass, you don't necessarily know who wins, like who would push who, until you look at the momentum.
So is it kind of like how
We'll get to that.
you could have like a car could have like I don't know 150 horsepower versus like if you have that in like a tractor or something like that, the tractor's gonna pull the car backwards because
Well, that's different. That's not a collision. That's a
yeah,
tug of war.
Yeah, I know.
If
but
you-
it's because
If you
of
did
the-
collide them,
Yeah, but I was thinking of like in the way of like how like it have to do with the like how it's geared to what it has to do with like,
yeah, that's a completely separate thing.
because like how
That tug
something
of war.
can be like set for it exerts its energy and speed versus like
You're getting into work energy and then power.
yeah.
Yeah, we'll get to that. Hold the pause on that.
Okay.
All right, what I want you to do. Looks like some of you didn't take time to start this, so make sure you follow along and are understanding what this is talking about. This, what's that? You don't understand? That's okay. We're gonna go over this one. This is relative velocity.
I have a
When-
question. Why are Blake and Carlos playing on a train?
I don't
It's
know.
moving.
They've received extensive train safety training. That's a mouthful.
And Angela just like.
And their author, I don't know. Again, we make up situations in
That's
physics.
always Angela, man.
You guys, relative velocity is when you look at the velocity relative to a specific viewpoint. So this question says, here's Blake, Carlos,
What's wrong with Carlos?
and Angela. She's like watching off to the side, like standing on the ground watching this.
Such an slow move.
Blake is running on the train car at 2 meters per second east. That's his velocity. It's a vector. 2 meters per second this way. The train car that they're standing on is also moving. It's moving at 5 meters per second to the east. Right? That's what all these, the intro numbers are. They're already labeled for us. The motion maps, I don't think I showed you these explicitly, but it's basically saying if this is Carlos over here, and we want to look at what's Blake's motion look like, well, to start, he's a certain distance away, but it's moving at a certain velocity. And then after 1 second, his position's here. It's closer to Carlos from where he's standing, right? They're both on the track, or the cart. He's running towards him. Every second, he gets 2 meters per second closer. Actually,
Motion map based on Angela.
Angela, thank you for correcting my mistake. So we're going to do from Angela. Angela is off to the side watching the train and the guys running on it. So
She's the safety instructor.
So it's going to look like
That's
this.
Dwight, and that's Andrew.
So every second, Blake is going to move a certain amount of distance. That's the position, and this arrow is, at that moment in time, that's how fast he's going.
And Angela is just Dwight.
Now, sketch a motion map of Blake's motion from Carlos' perspective. So again, it's going to start a certain distance away. In Carlos's eyes, is Blake running faster?
No.
Or is Angela's eyes, is Blake moving faster? In Angela's eyes. So this velocity from Carlos's perspective looks smaller. And he's covering less ground. When you have relative velocity, you need to pay attention. I almost made the mistake. Thank you for pointing that out, John. You need to know what perspective are you looking at the relative velocity. And think about it. If I'm Carlos, we're standing, say, end to end. We're both on the same platform, and Carlos is just running towards me. He's running towards me at 2 meters per second. Every second, he gets 2 meters closer to me. That's what I'm seeing from Carlos's perspective. However, if I change my perspective and I look at the same thing from Angela's point of view, she's standing here watching. The whole thing is moving, and Blake is running this way. Blake is going to look like he's going really fast. Because sure, he's running 2 meters per second, but the whole thing is also moving with him. They're moving the same direction, so that's how you know you can add the speeds. Every second, Angela watches the car move 5 meters because the car is moving 5 meters per second. And in that same second, Carlos went from here to here. He moved 2 meters on the track in that same second.
Maybe if it was going faster, this would make sense, but like, it would almost be like if you tried to go on a treadmill backwards because the thing underneath is also moving.
Well, no, but he's moving, like, because he's stationary, so they're both moving at the same speed.
Right, he's moving towards Carlos, and the train's, but the train's moving that direction.
Yes.
But the train is moving the other direction.
That'd be a treadmill. That's how on a treadmill, I can run 10 mile an hour. I can't probably, I don't know. But I don't go anywhere. Because I run 10 mile an hour and the treadmill goes 10 mile an hour. I don't move.
Yeah.
In this case, it's as if I go backwards. The treadmill is going this way and I'm going this way. I double my speed.
That's what I was talking about.
That's exactly right.
Oh, that's what's going on. Yeah.
Yes,
Okay, that's what I'm trying to
exactly.
figure out. Okay.
Every second, Carlos goes from here to here, 2 meters. But the whole train moves 5 meters. This whole thing moves 5 meters. So Carlos moves 2 meters, and this whole thing moves another 5 in that 1 second. So from Angela's eyes, he went from here 2 meters, and the whole thing moved 5 meters.
So 7?
So 7 meters. That means, what is Blake's relative or velocity relative to Angela? 7 meters per second. He's running, and the train is also running. Angela is standing and watching all this. So every second, he's moving 7 meters. Relative velocities, you add and subtract velocities. So, hopefully that makes sense visually. So if we use the diagram from part A, which is those motion maps, we answered that question. Determine Blake's speed relative to Angela. That means from Angela's point of view, how fast is Blake moving? Well, it was 2 meters on the cart, and the whole cart was moving another 5. 7 meters per second east. It asked for, I'm incorrect. It only said speed. We could have added east, and that would make it a velocity. Speed is just the number. How about if Blake went the other way? Remember, we still got Angela looking. So after 1 second, Blake moves 2 meters this way, right? But then the whole cart moves 5 meters this way. If he started here and ended here, how far did he move from Angela's point of view? He went back 2 on the cart, and the cart moved itself 5 meters forward. So what's this? Simple math. 3. That was all in 1 second. Whoops. Does this make sense? Right? Angela's watching this happen. That cart goes 5 meters in 1 second, but Blake on the cart moves 2 meters in that same second. So from start to end in that 1 second, Blake's position only changed by 3 meters per second. Which direction? When Angela's watching him run, is he actually moving this way, or is he moving this way? This way. He went 2 meters this way in that 1 second, but then the train moved 5 meters this way. So from start, he ran this way, 5 meters this way, to end. Yes, that's another way to think about it. The other way, I need to add my velocity vectors. 2 meters per second west plus 5 meters per second east. Because I have the cart's motion and Blake's motion, because I'm looking from Angela's point of view. Well, if east equals positive, this would be a -2 plus a +5 gives you 3 meters per second, either positive or east. Now, it might be a little confusing. It's a little hard to get a grasp on this to start with, these relative velocities, especially when you're adding motion. Does it make sense? Any questions? You want me to say something again? When you have relative velocity, you first need to know what's the perspective. What's Blake's velocity relative to Angela? Angela is my reference point. From where Angela's at, how fast does Blake move? What would be Blake's velocity relative to Carlos? Carlos is standing on the same train. He's on the train and watching Carlos run 2 meters per second west, away from him. From Carlos's eyes, how fast is Blake running? 2 meters per second. One, he's watching him. They're moving the same speed. You could also think about it. Every second, they both move in equal distance. So that's what the train's motion does. It changes both of them. It keeps them the same. But then Carlos is running the opposite direction at 2 meters per second. So then every second, they both move 5, and Blake moves 2. So in Carlos's eyes, Blake's only moving 2 meters every second, because they're in the same frame of reference. This is why when you're in a car on the interstate, you're moving the same velocity as the car is. However, if you throw something backwards, the speed of that object in the car is only however fast you threw it. But if you step outside the car and watched it through the window, it'd be the car's velocity minus how fast you threw it. Because now I'm looking at the whole picture. I watch the car go forward and that object, the ball, go backwards. So the total velocity from my point of view, I need to consider both motions because I'm looking at both of them.
Someone did an experiment like that once. They put like a cannon almost up to a truck.
Okay.
They drove 50 miles an hour this way and shot a bowling ball 50 miles an hour this way, and it stopped.
Yes. Does that make sense? So his example, they said they did an experiment where, like, if you had a truck. Again, I am an incredible artist. You don't have to tell me. I know.
Oh yeah.
Oh yeah.
Look at that ball.
If this is 50 miles per hour and the cannonball,
Oh, it's a.
what Ethan said is when this happens, if I'm standing over here watching this, my car is going to be moving 50 miles an hour, and I'm going to shoot my cannonball 50 the other way. If I'm watching the car move 50 miles in 1 hour, and a ball move 50 miles in that same hour in the other direction, what's my total displacement? 0.
So is the ball not going to move?
No, the ball would literally just, if you shot it, the ball would, like, drop.
Cool.
Wait, if you're like, if it's just, if it's pointing the opposite direction,
Yeah.
or it's pointing the other direction, same thing,
Well, it hit the back of the truck.
but not when it stops.
If you shot the cannonball this way,
Big cannon.
incredible. No need to applause. It's fine.
Everyone always thinks he's a gangster until the cannon.
And the cannonball is
Wouldn't it
50?
stay level with the truck and then
Yeah.
drop?
if you shot it. Let's see, how would that work?
Or if it's only going 50 miles an hour and it like wouldn't go anywhere, it wouldn't even come out the barrel.
Yeah, it like because you
Because
wouldn't
if
have
the-
enough force to get
Because
past it.
if the blast was only meant to cause it to go 50 miles an hour, that means the cannonball would just sit still, wouldn't it? And it wouldn't even come out the barrel.
Yeah, because it would have to.
You'd have to have more than 50 miles an hour to push it out the barrel.
Right?
Special experiment on Tuesday.
So this gets really hard because you have to look at like air resistance. You can't just assume like it exits at 50 and stays that speed.
Well, can we just assume there's no wind and your only air resistance is the air resistance
We're in a vacuum.
of 50 miles an hour?
Actually, if you were physically able to shoot this ball from cannon 50 miles an hour, this would actually be going 100 from this perspective.
Right.
Because my launch is based on my cannon. If I can make my cannonball move 50 miles per hour from my cannon that was launched, well, if my cannon's already moving 50 mile an hour and I push it another 50 mile an hour, if I'm watching all of this, that cannonball is going to be moving 100.
Well, how? How do we just stop?
No, because this velocity is relative to what I'm launching from.
Because if it's backwards, then it cancels.
So relative velocity of the cannonball. So the cannon.
What are you talking about the cannonball not even moving at all?
Relative to car equals 50. If I'm looking from the car, if I'm in the car and I watch it at 50, I'm going to see 50 mile an hour.
Right.
If I do the cannon relative to outside, it's 100. Because I'm watching a car move 50 and a cannonball get shot out another 50. Because my relative motion, I'm adding my velocity vectors.
Well, then how come if you shoot in the other direction, it just doesn't?
Because when I watch from outside, I see 50 and 50. If I add those two vectors, positive 50 and negative 50, 0. That's an excellent question, and I'm glad you asked that because that's directly related to what we just did. It's okay if it's confusing. We'll touch back Tuesday. Thank you, guys. Have a good weekend.
That means theoretically.
It's a good question.
Theoretically.
Oh, I hope they can see that.